Okay, we're live. All right. Okay, so we're going to go over section 5.4, part 2, FTC part 2. So the key thing here for part 2 of the fundamental theory of calculus, it's stuff that we've already done before. So we've been assuming that f is continuous, right, on a closed interval from a to b, and capital F represents any antiderivative. So for example, say f of x were 2x, then what would capital F of x be? No, you're doing the derivative. It wouldn't be 2. It would have to be just x squared. Because what happens is that you increase the exponent by 1 to make it 2x and then divide by 2, but the 2's cancel. And of course, it's a plus c. The thing is that the plus c's actually get canceled out when you do the definite integral, because the whole purpose of doing the definite integral is to take the antiderivative, plug in b and a, and then subtract. So again, the whole purpose here is to antiderivative, plug in x equals b and x equals a, and take difference. That right there. Nice, Dane. Dane just got his Arizona tea. So you're in the video. Good. So anyway, we know this, right? To do a definite integral, you take the antiderivative, plug in x equals b and x equals a, and then take the difference. That's FTC part 2. And we're going to practice that in the next example. Before we do that, it's good to note that there's certain notation that you want to be comfortable with. So when you do the antiderivative, sometimes some people will use this notation where they'll do the antiderivative and then they'll like put a little bar and the limits of integration to show that they're about to plug in a and b. So it's kind of an intermediary step. Or some people will use like a bracket around the antiderivative and then put a and b on the right side of the right bracket, again, to show that they're ready to plug in a and b. So let's look at example 7. So what's the antiderivative of secant squared theta? Good. Okay, then, so that's my intermediary step, right? I took the antiderivative, I'm ready to plug in, so now I plug in. So what's tangent of pi over 3? Remember unit circle? It's root 3, good. Now if you forgot, what I usually like to do, first of all, realizing that pi over 3 is 60 degrees, because remember pi is 180, and what's a third of 180? 60, right? So, of course, you would have to know your special right triangles, like if that's x, that's 2x, and x root 3. And you're doing tangent, which is opposite over adjacent of 60 degrees, so what happens to the x's? Cancel, so you get root 3. The other one's a 45 degrees, right? Pi over 4 is 45 degrees. You guys should know for a 45, 45, 90 triangle, the legs are identical, right? So when you take the ratio, it's just 1. So that'd be an exact answer, I guess, for that definite integral. You can plug in the calculator, but the calculator is going to give you a decimal, but you can always verify by just also computing root 3 minus 1 in the calculator. It's like 0.73, I think. So, okay, any questions about how example 7 works out, FTC part 2? So again, FTC part 2 is basically just take an antiderivative, plug in b and a, then take difference. Okay, we're going to do more of this, but we're going to kind of look at a different perspective. We're going to talk about area. And we're going to delineate between net area and total area. So net area is what we've been doing all along. That's what we've been doing so far, which is just a definite integral. That's all. Just a definite integral. So anything below the x-axis is negative. Anything above the x-axis is positive. Total area is new. That's kind of a new concept here. Basically, everything is treated as positive. So all areas are positive. So if we're integrating from A to C in this example here, if you want the net area, what would you say? Yeah, it'd be 7 plus negative 2. How about the total area? It'd be 9, because what you want to do, it's almost like taking absolute value for total area, absolute value of negative areas. Well, what is that? I'm sorry? Well, what do you mean I include a negative? Right, but you make it positive. Right. And so basically, so another way to think about too, which we'll talk about in chapter 6, I believe, is distance versus displacements. Displacement actually would represent net area, because you're looking at the change. Distance would actually be total area, if you're looking at the total distance you've traveled. So, okay. Displacement, which we'll explore in chapter 6. That's an application of this stuff. But for now, I just want to kind of introduce the idea of total area versus net area, and that you guys know the difference between the two. So let's look at example 8. Now, if you don't see a specification, so if there's no specification, assume it's total. So if they say, find me the area, I don't know why that's the case. Maybe some calculus teachers got together and figured, okay, that's what we're just going to do. So I don't know. But if you don't see a specification, assume it's total area. So in this case, we're asked to find a total area between the curve and the x-axis from -1 to 4. So you don't want to do this. Don't do that, because that's going to get us net area. And it's pretty obvious from the diagram that there's one region that is below the x-axis. So what should we do instead? 2 integrals. So you're going to probably do one from about -1. Well, obviously we're going to start at -1 because that's the way we define the region as left endpoint. Up to what upper limit? 2, good. Remember, 2 is the x-intercept. Yeah, because that makes y 0. So what you could do is you could solve for it algebraically if you needed to. I mean, I think it's pretty obvious in the diagram, but of course we're not going to deal with -2 because that's outside of our defined interval. So we'll go from -1 to 2 of x squared minus 4 times dx. By the way, I'm going to put a little negative to the left of that integral. Why? Because without it, it's going to be negative. With it, it now will be positive. Or if you like, you could put an absolute value around the whole integral. Totally up to you, whatever you prefer. But you need to guarantee that that definite integral is going to come out being positive, because we're asked to find its whole area. And then if I keep moving, what's the other integral I'm going to write? From what to what? Well, we stop at 4. From 2 to 4. What was that? Well, no, because then I don't know. Then it's infinite area, right? So, so we don't really look at that. Not for, yeah, because then it wouldn't be definite, right? Yeah, we will talk about indefinite integrals where we don't have limits, but that's just more just finding an expression. But we'll worry about that in the next chapter. Anyway, so let's work these out. So if we find the antiderivative, which you guys should be comfortable with, I'm going to focus on the right integral for now, just because I feel like it. What's the antiderivative of x squared minus 4? X for 3 from 2 to 4. Okay. And how about for the other one? Well, same thing, right? But you're going to put a negative. And actually, just be careful. I'm probably going to put a parentheses as well. From -1 to 2. Okay. Now I'm going to work it out. Again, if I work out this side, I'm plugging in 4, so that's 64 thirds minus 16 minus 8 thirds minus 8. If I plug into the other side, gotta be careful here. That's 8 thirds over 3 minus 8 minus -1/3 plus 4. Yeah, you gotta be really careful if you're doing this by hand, which is why it's always good to confirm with the calculator. I think I did that right. Okay. Okay, now the fun begins. Now we actually have to kind of combine everything. So that's going to be 64 thirds minus 16 minus 8 thirds plus 8. And I'm going to be really careful with this one. 8 thirds minus -1/3 is actually 3. And -8 minus 4. So that's 9 minus 8 plus 56 thirds. And hopefully we did this right. Actually, I know we did it right, because I've done this twice already. So 59 thirds. That would be the total area. Which kind of makes sense, because we're, again, treating everything as being positive.
Do you want it to be my fraction?
I don't care. Or it could be, you could do fraction with decimals or mixed numbers. You could also write 19 2/3. Or you could write 19.667, whatever, So, okay. Now, what if I did find the definite integral from -1 to 4 instead? I'll tell you right now what the answer would be. It would be 5 thirds. That's the net area. If you were to work it out, you would get 5 thirds. But the reason why I know it's 5 thirds is because this one right here was -9. That was based upon what I saw from that integral from -1 to 2. And then, of course, we made it positive by multiplied by -1. This over here would be 10 2/3. So that's what happens there. Okay. Any questions about what we just did there? Nope. All right. Okay. You could also, if you're lazy, or efficient is a better way, or cunning, clever, you could use a calculator. That's numerical integration. So using the calculator. And here's how you could do it. Does anyone recognize this function here? What that is? That's going to be y equals s of x squared minus 4. The reason why is because it's a transformation, right? So off to the side here, what's an App's value transformation? Basically, you reflect any portion below x-axis over. This you guys should know from pre-calculus, but in case you guys forget, that's what absolute value does, is a transformation, right? So what you've done is now your entire region is above the x-axis, right? Now it's positive. So you could just write the total area as this, from -1 to 4, with the absolute value of x squared minus 4 times dx. That's just going to be all this right here. This, of course, is net area. So, and of course, this is total area. So, okay. So let's use a calculator. And actually, I'll just show you. I have this really cool calculator app. Yeah, it's pretty cool. So if I were to alpha window, and hopefully you guys can see what I'm doing. And I'm going to actually, I'm in the old operating system. Let's try that again. Alpha window, option 4, from -1 to 4. And kind of give it a little time, and we get the same thing. So again, for lazy people, if you don't want to break up the two integrals, but it's good. It's a good way to check. You know, it depends. If I don't, and you have a calculator, you should know how to break it up. You should be aware that can be broken up. So yeah, you still get the same thing. 19.667. So in essence, the total area can be given by this, from A to B, absolute value of f of x times dx. That's the total area. Don't confuse this with doing that. What do you think that would do?
Well, that doesn't mean it's necessarily like everything above the x-axis.
Right. What it's going to do?
Oh,
It won't transform it. So basically what this will do is just the absolute value of net area. That's all it will do. Just outside net area. That's it. So if I did it for the previous example, I would just got 5/3, not 19.667. So it doesn't transform the graph that we want the way we want it to. Oh. You got it? Okay, great. Okay. What time does bell ring, by the way? Okay, so we'll be able to talk about this just for a little bit. No, we're not chilling out. We're doing this one right here. Okay, we're just going to briefly talk about, and we'll do this in more detail next time in class. So this problem right here is a problem that shows up often on AP exams. Actually, I think it shows up pretty much every year. What they're doing is they're defining h of x as a definite integral from 1 to x of f of t times dt. That's just area accumulation. Like, for example, what if I want to find h of 2? Then you replace x with 2. You guys should know that. On the next page? Oh, okay. Then you guys just watch. That's fine. Yeah. I made room for myself. So, but if you look down here, and again, yeah, don't have to write this. You guys can just watch. But hopefully you guys see what I'm doing is that if h of x is defined as a definite integral from 1 to x of f of t times dt, we know definite integral being area, right? If I were to say x equals 2, I'm integrating from 1 to 2, right? Well, that's integral from 1 to 2. What is that area right there? Which is 1. So this would equal 1 then, of course. And that's something that they could ask. You know, they want you to make sure you understand what that means. That, oh, I'm supposed to find area. So let's look at this. We'll probably just do part A. If we have time for part B, we'll sneak it in. But if I look at part A, okay, so now they give us a different function. They call it G. And it's actually very similar to H, but they start at -4. So again, G is still an area accumulation function. And here's what they want us to find. G of -1. G prime of -1. And of course, G double prime of -1. Now, G is basically just finding area. From -4 to -1 on this graph. By the way, this is a graph of f. It's not a graph of G. But G is defined as a definite integral of f, so wouldn't I just want to just find this area here? How do I find that area? Smart. Yep. Yeah, and it's going to be negative, by the way. It's going to be negative. Area of the rectangle, I think, is 6. Area of the triangle is 1.5. Is -7.5. So that's that one. Let's look at g prime negative 1. Now, here's where it gets interesting. And this is the part that I really want to drive home. It's kind of hard to see what I wrote, but if I take derivative of both sides with respect to x, right? So derivative of g, we call it g prime, right? What's the derivative of the definite integral? It's just going to be f of x. Yeah, so g prime of x is actually just f of x. Remember, that's FTC part 1. That's what's happening there. So, really, I just want the y coordinate at x equals 1 for the graph of f. That's all I want. What is the y coordinate there? Negative 2. Okay. What if I do a second derivative? It'll be f prime, right? Okay. So in this case, what I really want is the slope of the tangent line. So you guys should know that, if you have a graph of f prime is the slope of the tangent line. Of course, at x equals negative 1 for the graph of f. Now, what is the slope of the tangent line there? Does not exist. Yeah, you have a corner. That's what we talked about. So we'll pick this up again next time in class.